So today we're going to be looking at this really cool theorem called the six-color theorem. And what this theorem says is every planar graph is six-colorable. So if we can draw a graph in such a way where the edges don't cross each other, then we can color each of the vertices in a way so that no two adjacent vertices get the same color. Now, this is a much weaker version. We can actually do way better than this. So there are theorems called the 5-color theorem and the 4-color theorem. So the best we can do is 4-color. So it turns out that we actually can color a planar graph using at most 4 colors. But that is an extremely difficult thing to prove, and it's done by a computer. There's like thousands of cases, so we can't tackle that. But we can tackle the much easier 6-color theorem, even though the result is not as strong. All right, so let's start our proof. So the way we're going to do this is we're going to prove this by induction on the order of the graph. So by induction on the order, number of vertices of a planar graph. Okay, so we're going to need a base case. An easy base case will just be a single vertex. So clearly, if we have just a graph with one vertex, we can color it using, green, which is we colored it with less than 6 colors, and no two adjacent vertices will share the same color. So as a base case, a graph with a single vertex is 6-colorable. A graph with a single vertex is 6-colorable. So now we're ready to move on to our inductive hypothesis. So we're going to assume that all planar graphs of order n are 6-colorable. So we'll say let n be greater than or equal to 1, and assume that all planar graphs of order n are 6-colorable. Okay, and our inductive step is we're going to examine a graph of order n plus 1, and we want to show that that graph is also 6-colorable if we assume that all planar graphs of order n are 6-colorable. And also, I didn't write it, but we're assuming that n is an integer or a natural number. Okay, so we're going to let G be a planar graph of order n plus 1. So since G is planar, we know that G has a vertex of degree at most 5. That's one of the results that we derived about planar graphs. So all planar graphs have a vertex of degree at most 5. So we could say, since G is planar, G has a vertex of degree at most 5. So we'll call that, so G has a vertex, we'll call it V, of degree at most 5. So we're going to want to use our inductive hypothesis here, that we're going to want to use the fact that if we have a planar graph of order n, then we can 6-color it. So G is a planar graph of order n plus 1, so if we delete this vertex V, we'll have a planar graph of order n, and we can use our inductive hypothesis to say that that graph is 6-colorable. Okay, so by our inductive hypothesis, G minus V is 6-colorable. So by our inductive G minus V, by our inductive hypothesis, G minus V is 6-colorable. All right, so we deleted V, and we were able to color the rest of the vertices. So the question we want to ask is, can we color V? And the answer is yes, because V has at most 5 neighbors. All right, so let's draw a picture of this. So if we have this vertex V, it has at most 5 neighbors. Right, so we deleted V and we were able to color all of these. So let's say this one was teal, this one was blue, this one was red or pink, this one was green, and this one was yellow. So right, when we deleted V, we colored all of these vertices. But now that we add V back, the idea is this vertex V has at most 5 neighbors, and we're trying to color all the vertices with 6 colors. So we have an available 6th color to color V, because it has at most 5 neighbors. We will always, if we're using 6 colors, then we have an available color to color V. That's the idea. So since V has at most 5 neighbors in G, we have an available color for V. So since V has at most 5 neighbors in G, we have an available color for V. And what does that mean? We colored in V, we colored in all the other vertices when we deleted V, so G is 6-colorable. Alright, so that completes our inductive step. We've proved that if all planar graphs of order n are 6-colorable, then all planar graphs of order n plus 1 are necessarily 6-colorable. So we can conclude by induction that all planar graphs of order n are 6-colorable. So conclude by induction that all planar graphs of order n are 6 colorable. And that is a proof of the 6 color theorem.